What's up everybody, hope you guys are all off to a wonderful day. My name is Akram, and in this video we'll be using React 3 Fiber to explore how we can create shaders. Now shaders is this other sort of world within Three.js. Three.js provides this blocking element that allows you to create 3D elements on the screen, and then shaders lets you to get full customization on what you want to really display. Now here's some websites using shaders and Three.js to create these impeccable different scenes. Some basic things to know about shaders is the fact that they're not written in JavaScript. They are written in GLSL. It does work on the GPU, so it isn't running code or different sort of data on the CPU. It does utilize the computer's GPU. And the reason it runs on the GPU is because it needs a lot of processing data to process all the information that is being written. Now shaders are very, very difficult to learn. And in this video, you'll definitely not understand all the concepts I'll be going through. And if you do want a terrific course that I truly recommend, it's by Bruno Simon. He has an entire 3ds journey, which just takes you through the different sort of modules and courses you need to get good or even excel your skills in Three.js. And in there, he has a section related to shaders. It is an incredible course, and if you want to sign up for it, definitely go for it. I cannot recommend it enough. So in this video, we will be creating this wavy image you see on the screen. This is a very common style throughout different websites. Like when you hover on an image, it waves or transitions to another page and it does that waving animation. Yikes, this guy talks way too much. If you guys look in the description, there is a code sandbox link where this project exists. And there's also a written tutorial through a Notion doc. So be sure to check those two out if you can't stand hearing my voice. Okay, let's just wrap up this intro then. Okay, that's gonna do it for me. If you haven't subscribed, go ahead and subscribe. Be sure to like, and don't forget to comment if you have any questions or concerns. He's getting a little impatient, so I'll put it back. Oop. Anyway, take care guys. Have a good one. Okay, to get started, let's go ahead and run npx create react app, and then we can name our app whatever we want. I'll go ahead and name it r3f-shader. This might take a bit, so I'll go ahead and skip it. Once that's complete, let's go ahead and clear out the terminal. We need to cd into our directory. And then if I ls, we can see we've got a bunch of files in there. Let's go ahead and clear that. And now I need to install the packages that are needed. I'll first install 3, which is the JavaScript 3D library. I'll need to install React 3 Fiber, which is a React renderer for Three.js. Then we'll need to install React 3/dry. And this provides useful helpers and different components when working with React 3 Fiber. We'll need GLSLFI, which is a Node.js style module system for GLSL, Babel plugin GLSL, which is the Babel plugin for writing GLSL code, and finally GLSL noise, which allows us to use different noise functions rather than needing to write them from scratch. Once that's complete, let's go ahead and write code to open up VS Code. Now in VS Code, let's do two things. Let's go ahead and install 2 packages that will help us write better GLSL code. The first one is GLSL lint, and the second one is GLSL literal. Once we've got those installed, we can switch back to our app.js, and let's open up the terminal and run npm run start to get our development server going. I'm going to be splitting the screens between the code and then the website just so that we can get a better idea of what we're working with as we're coding. And now we can start coding. I'm in app.js, and what we need to do is just get rid of everything. We can leave the import of the CSS file and the export default of app. Don't worry about that. We'll create an app function here in a bit. First thing I need to do is import canvas from React 3 Fiber. Canvas is the object where we start to define our entire React 3 Fiber scene. Everything Three.js related is written inside of our canvas component. Next, let's go ahead and create a function called scene. Inside of our scene, we can go ahead and return a canvas component. We'll also want to create another function called app, where we'll go ahead and return our scene. Now, if we go ahead and save, you can see that we just have a blank screen. Nothing's really been done here, and this is just very boilerplate information. Let's go ahead and get a plane displayed on our screen. Inside of our canvas, we'll want to go ahead and create a mesh. And inside of that mesh, let's go ahead and add a plane buffer geometry. Now, this plane buffer geometry is coming straight from Three.js, and there's no importing needed. It does take in some arguments, and the arguments that it does take is 2 values in an array, and those values are width and height. We'll go ahead and set the width to a 3 and the height to a 5. In our screen, we can see that we have a tiny gray box in the top section. Now, this entire canvas is very small, and what we want to do is allow it to cover our entire screen. The canvas component is automatically responsive, but what we need to do is jump into our app CSS, and what I'll go ahead and add is an asterisk and assigning everything in our app to a box sizing of border box. Next, we'll target the HTML, body, and ID of root, setting the widths and heights to 100%, a margin of 0, and a padding of 0. If we save that, you can see that our entire plane is a lot larger and our entire canvas is covering our screen. Now, if we wanted to change this color, what we could do is add a mesh standard material. And mesh standard material allows us to pass in a color prop, which will let us change the color of our geometry. We can pass in a color of light blue, but what you'll notice is that it's just black. And the reason that is because there's no light. If there is no light in our canvas or sort of in our world, then color doesn't matter because light is what allows us to see color. We can add a point light outside of the mesh while still being inside the canvas, and we could position this point light. The position takes an array with 3 different values, X, Y, and Z. We'll go ahead and set 10 to all of them, and now we can see that we have a light blue plane. You can change the values all you want, and that will just change the position of the light, and it will allow our point light to hit our geometry in different directions. There are helpers out there to where you can add orbital controls to kind of zoom out and move around the canvas, and there is light helpers that will allow us to see where our light is positioned. We don't need any of that stuff, and you can always find in the documentation if you do need some help. Okay, so we've got some very basic scene here to where it's just a plane with a light and a color. Next, let's go ahead and start working with shaders. Now, a shader is a small program written in the GLSL language that runs on the GPU. You may want to use custom shaders if you need to implement an effect that is not included with any of the built-in materials and have the ability to create very unique things. To use shaders in React 3 Fiber, there are several ways to do so. We can just target the shader material from 3, but we did install this helper package called Dry, which has a shader material function that we can use to our advantage. Let's go ahead and import shader material from React 3 Dry, and then we'll also want to import GLSL from Babel plugin GLSL/macro. Next, let's go ahead and create a wave shader material function, and what we'll provide it is a shader material. Now the shader material will receive 3 arguments. The first one will be a uniform, which will be an empty object for now. The next one will be a vertex shader. What we'll do is add GLSL with template literals and leave it empty. And the third argument it'll receive is a fragment shader. Now, let me go ahead and describe what each of these items are. Now, uniforms provide us a way to send data from JavaScript to our shaders. We can use uniforms in both the vertex and the fragment shader. Some use cases would be if we want to pass mouse position data, time information, colors, textures, etc. The vertex shader is a shader that runs first. It receives attributes and manipulates the position of each individual vertex. Essentially, it positions the vertices of a geometry to create a shape. The fragment shader runs after the vertex shader has defined our geometry's shape, and it sets the color of each individual fragment or pixel on the geometry. So on the left, we have a geometry where the vertices are already placed. We then color each individual fragment or pixel, and then have the ability to blend them to create different colors. So now we need to be able to use this wave shader material in JSX. To do so, we will import the extend function, which will allow us to use this wave shader material as a JSX component. We'll go ahead and add curly brackets to bring in wave shader material. And now we can use wave shader material in JSX using a lowercase w in the beginning and then shader material. Go ahead and replace our standard material with our wave shader material. Now we'll get a blank screen because our wave shader material hasn't defined any vertex or fragment shader. We'll go ahead and get started on the vertex shader because we want to define our positions and the different vertices. I'll go ahead and create a function with a type of void since we're not returning anything. We'll set the GL_position to a projection matrix multiplied by a model view matrix. multiplied by a vec4, passing in a position and a 1.0 as its second argument. Okay, pause the video right there. What in the hell did we just write? Let's go back in our project and take a look. I'm gonna first describe the GL position. Now the GL position already exists and it is defined, so we don't need to import anything. The GL position will ultimately contain the position of the vertex that we see on the screen. We then have our matrices. There's 3 different types of matrices that we use. The first one is the model matrix. It applies all transformations related to our mesh. Think of scale, rotation, and movement. All of that is contained and applied to the position. Next, we have the view matrix, which applies all the transformations that are related to the camera. So when we rotate the camera, zoom in, zoom out, move the camera around, all of that information is contained and applied to the position so that it correlates with our mesh. And finally, the projection matrix, which transforms all the collected coordinates and displays the final clip space. Now, I didn't use model matrix and view matrix on their own. We have another matrix called model view matrix, which just combines the model matrix and the view matrix so that you don't need to write them separately. Okay, so what is that vec4 then? Well, that is a type, but before we get to that one, let's cover more basic types. The very basic ones include float, integers, and booleans. Floats are positive or negative decimals. Same for integers, they can be positive or negatives, but they must be whole numbers. And then booleans are just booleans, true or false. Now in JavaScript, we use something like vars, const, let. But in GLSL, we just define the type, the variable name, and then whatever we assign it with. Now additional types include vector2, vector3, and vector4. Vector2 allows us to store 2 values. Think of x and y coordinates. So in our example, we've got vec2, which is a type. The variable name is an a, and then we can store the floats 2.0 and 4.0 inside the vec2 as an x and a y coordinate. Now keep in mind, they're not always x and y's, but the x and y is just a perfect example. Next, we have vector3, which stores 3 values, x, y, and z. Now the x, y, and z coordinates are a great example, but also think about how we can store values of color, RGB. With vec3, we can pass in 3 different values like you see, or what we could do is combine vec2s inside vec3s. So in the combination example, we've got a variable a, which is a vec2 of 2 different values. And then we have variable b, which is a vec3, which takes in 3 different values, but we can use that a so that it has 2.0, 4.0, and 6.0. And finally, vector4, which allows you to store 4 values, x, y, z, and the last one being w or a. With this one, similar to how vec3 is, where we can take a vec2 and use it within the vec3, we can take vec2 and 3 and use them in the vec4. Okay, a little confusing at first, but you'll definitely get the hang of it. The whole purpose of these is just a type that allows us to store different amounts of values, either being 2, 3, or 4. Okay, now back in our project, let's get some color going. That will require us to jump into our fragment shader. Inside the fragment shader, we can create a main function with void, and then in here, we assign gl_frag color with a vec4 of 0.0, 0.4, 1.0, and 1.0. Again, remember we're using 4 different values because it's a vec4. Now because we are writing shaders and it runs on the GPU, we need to refresh our page. Let's go ahead and refresh the page, and now you can see we have a blue box. Now how do we get this blue box with this GL frag color and this vec4? Well, vec4, again, like I mentioned, it can be used as X, Y, Z, or W, or it can be used as RGBA for red, green, blue, and then alpha. Now I'm going to go ahead and change the colors around so that we can create different colors on the screen, and you can see as I edit these different values, the color is changing. The GL frag color is very similar to that GL position, except that it represents color. You can see we could also play with the alpha and drop it down to 0.8, which just decreases the opacity of our color. Feel free to play around with the different values and see what colors you can create. Okay, perfect. So you got your first shader done. Now let's work with the uniforms. Let's try to pass a color prop from our component and then use it in our fragment shader. To do so, we'll need to import everything as 3 from Three.js And then in our uniforms, let's go ahead and create a property called uColor. The reason we're using the lowercase u is to help us identify that it is a uniform. We'll go ahead and set this to a new 3.color, and then we'll pass in 3 different values, RGB, setting them all to 0. This will give us a default color for our uColor property of black. Now to use this uColor property, what we'll do is write the following in our fragment shader. We'll say uniform, giving it a type of vec3. Again, we're using vec3 because it is 3 different values. Had we used a vec4, we'll need to add an alpha, but we don't want to do that. We'll use vec3 and then uColor, which is the name of our property. This is pretty much how you use uniforms. We can then replace the first 3 values with uColor, and then when we refresh the page, you could see it's black. If we want to change the color, we'll go to our uColor property, and then we'll change the first value to 1.0, which will turn it red. Since it is RGB, you gotta remember that changing the first value, which is a red channel, to 1.0 will max out that red color. I'll go ahead and set it back to 0.0 so that we can get the black color back. And what I want to do now is pass in a uColor prop and set it to anything. We'll go ahead and set it to hot pink, and you can see that it updates automatically. Remember, the uColor has a default of black, but if we pass a prop, you can see that it does override it. If we switch it to green, you can see we get a green color, and if we remove it, it gets defaulted back to black. I'll go ahead and put the uColor of hot pink back. And to describe it one more time, you can see we are passing in a uColor prop. In our uniform, we are describing that property, and then we're importing that property in our fragment shader with uniform vec3 describing its type of uColor, and then we can use the uColor in our main function, passing it in the vec4 with a 1.0 of alpha so that it is 100% opacity, and then assigning that to our GL frag color. Now we've got a basic color, but if we wanted to create a gradient without any sort of helper functions, how could we do that? Well, first we need access to our coordinates. Each geometry already has coordinates that are defined to help us display different colors and textures on our geometry. These coordinates are called UV coordinates or UV mapping. Access to these UV coordinates are only available in our vertex shader. The issue here is we need to access these UV coordinates in our fragment shader. To do so, we'll need to use something called varying. Varying allows us to send data from the vertex shader to our fragment shader. To do so, we'll need to define a varying vec2 of VUV. We choose the name VUV because the lowercase v lets us know that this is a varying. And then inside our main function, we'll need to assign VUV to UV. Again, remember, we don't need to define UV because UV is already globally accessible only inside the vertex shader. Now to access VUV in the fragment shader is simply write varying vec2 VUV, similar to what we wrote above in the vertex shader. Now remember, VUV is equal to UV. And if we want to create a gradient now, all we do is inside the vec4, write VUV dot x for the x coordinates times uColor. And now you can see we've got a gradient. If we switch the x to y, you can see we have a gradient from the y-axis. And here we can just kind of play around with the math. So we can just divide and it'll turn to this color. If we multiply, it'll turn back to our pink color. If we add, it'll go from the light gradient rather than the dark one. So really you could just play around and experiment. Again, when it comes to math, I am not good. So giving you the exact values of what's occurring, don't look at me. I am just experimenting and having fun with it. I'll go ahead and set it back to normal. And what I'll do next is get rid of the .x and the uColor. I'll leave VUV, 1.0, and if we refresh, it's blank. So something's wrong here. Remember, VUV returns 2 sets of coordinates, and since we're using vec4, in total there's only 3 coordinates if we leave it as is. Let's go ahead and add a 1.0 for the third argument, and now we've got this color here. Now if I add a .x, you can see it goes back to blank because it's an error. Since .x will only return the numbers or the values on the x coordinates, we'll need to add a additional value because now we have 4 different coordinates for the vec4, and we could pretty much play with it. And we could change this to 0.4, and now we've got like a very blue to purple color, which is very nice. Again, go ahead and take some time and experiment. You'll learn a lot just from playing around and learn a few cool patterns. Let's go ahead and reset this back to what we had it initially. What I want to do next is to play with a bit of movement. Let's aim to move the gradients from left to right, from going to this hot pink to black, hot pink to black. Scroll to the top and we'll import React, useRef, and suspense. And from React 3 Fiber, let's go ahead and import useFrame. We've used useFrame a lot in the past on this channel. What it is a Fiber hook that lets you execute code on every frame of a Fiber's render loop. It's the perfect hook when working with animations. Let's go ahead and create a new uniform called uTime and set it to 0. This uniform will store the amount of time it's taken since our scene has been established. Now, when working with use frames, they must exist in their own component, not relative to the canvas component. So this use frame cannot be in the scene. We'll need to create a wave component, grab the mesh, put it in the wave component, and then render this wave component in the scene, and therefore we'll be able to use a use frame within the wave component. A little bit confusing, but they do notify us in the documentation or else it'll fail. Now be sure to wrap this wave component with suspense, setting the fallback to null, just in case it doesn't load. And now we can move on to the use frame. Before we use the use frame hook, let's use the useRef hook to create a reference for our wave shader material. I'll go ahead and create a const ref, setting it to a useRef hook, and then we'll use useFrame. And useFrame will take a callback function, and for this function we're going to pass clock. Be sure to use destructuring to access the clock. And before we return anything in this frame, we need to set ref equal to ref in our wave shader material. Now what we can return is ref.current to access the wave shader material .uTime, which will allow us to access this shader material's uniform that we defined in the uniform section. And we'll set the uTime to clock.getElapsedTime. GetElapsedTime will get the number of seconds that's passed since the clock started. A clock starts once the scene has been rendered via Three.js. Okay, perfect. Go ahead and save that. And now let's scroll to the top of a fragment shader. And what I want to pass in at the very top is a precision medium P float. This will allow us to determine how much precision the GPU uses when calculating floats. We'll go ahead and use medium, but there's low and high. To access the uTime uniform, we write uniform float uTime. Now to use this uTime to create some movement, we want to manipulate the uvu.x value. So what I'll do is wrap it in a sine, and inside sine, I'll do vuv.x plus uTime. Now, remember, if you could recall way back in the day when you were learning about trigonometry with sine, cosine, tangents, all that good stuff, in our case here, when we write sine, this is a method that's returning a numeric value between -1 and 1, which represents the sine of the angle given in radians. Now, in terms of exact mathematics, I am definitely not the person to tell you, but an idea here is we are using vuv.x or y or whatever we use in terms of the coordinates. We're adding a uTime, which uTime is continuously changing through our use frame, dependent on how long our app's loaded or has been displaying for. And then sine is returning a value from -1 to 1. So that it is allowing us to go from from -1 all the way to 1, changing the color, and that's how it creates this effect of moving from a certain direction, from going to black, going to the hot pink that we described. It's pretty confusing, but once you continue to play with it, it'll make a lot more sense. Like I mentioned, shaders are extremely difficult to pick up and master. This will take a long time for you to be able to understand everything that is going on in the background. But now we can move into our next step to where we actually start incorporating this movement and wavy effects and our textures. So let's go ahead and scroll down now. And what I want to do with our plain buffer geometry is edit the arguments. For now, we're using 3.5 for the width and heights. Let's change that to 0.4 for the width, 0.6 for the height, and then we'll pass in these two additional values of 16 and 16. Now these are the segments, the width and the height segments that I had mentioned earlier in the video. They are optional, but we need them in our case now. Since changing the sizes, it's gotten a lot smaller for our rectangle. What we'll do is adjust the camera. Canvases always come with cameras, so we can edit the camera prop directly in the canvas. And what we'll do is set the FOV to 10. This is the field of view. You can set it to whichever value you want to zoom in the camera, or you could change the position of the camera to move the camera closer to the object by setting a position and passing in 3 different arguments of X, Y, Z. You can see here I'm playing with the FOV, setting it from 10 to 5 to 0 to 20. Really, it's up to you, whichever one best prefers your taste when you're working with the geometry. If I add a position and change the Z index, you can see that we can move the position back and forth, but the default is 0.005 for us here because it matches perfectly with the FOV of 10. I'll go ahead and leave it, but we can remove it and it wouldn't make a difference. What I'd like to highlight next is the width and height segments of the plane buffer geometry, those 16 values in the arcs. I'll pass a wireframe prop so that we can get a better look. You can see that when I do pass it in, we've got these different fragments or pixels in a 16 by 16 ratio throughout our entire widths and heights. I can change these values and you can see that the amount of blocks in each width and or height changes. So this is extremely important when you're working with the waviness factor or working with the vertex shaders. This is extremely important to get the right values because with the fragment shader, it'll run the GLSL language or data in each individual fragment or pixel that you see on the screen. And the same goes for that waviness factor. The more segments we have, the more smoother it is. Now let's scroll up to the vertex shader, and since we're going to be working with floats in our vertex, we'll want to also add the precision medium P float so that we can target the performance of our GPU. Next, we'll need to use our uTime uniform, and we can do that by writing uniform float uTime. Now before we continue, a lot of the help that I got here was from this article here on code drops by Mario Carrello or Carrello. I'm not really sure how to say the last name, either if he's Spanish or not. But he had written up this article which talks about how to create this exact same effect on code drops. So I'll have it linked below, and I'll also have Mario's socials down below. So go check him out. Now, if you could recall, we did install GLSL noise, which allows us to have access to a lot of noise related functions. This is extremely handy because these functions you could copy and paste them from the articles or even on GitHub, but they're about like 100 lines of code, and it would just be much better if we could just import it through our package. To do so, we'll use hash pragma glslfi semicolons snoise3 and set that to a require glsl-noise /simplex /3d. This will allow us to use this snoise3 function without actually needing to have written any of it. Next, in our main function, let's go ahead and create a POS variable and set that to position. This type will be a type of vec3. We'll then create a noise frequency, setting that to 1.5. Again, it's going to be a float since it is decimals. And then we'll also create another float of noise amp and set that to 0.25. Now we'll create a vec3 of noise position and set that to a vec3 of pos.x multiplied by our noise frequency and add a uTime. For our second argument, we'll pass in a pos.y, and the third one we'll pass pos.z. So these are 3 different values because we are using a vec3. We can target the pos.z directly and run a plus equal snoise3, passing in the noise position variable that we had created above and multiplying this by a noise amp. Now for our GL position, we'll replace this globally defined position attribute with POS, the one that we defined at the very top of vec3 POS. Let's go ahead and save that, and if we refresh, you can see that now we are starting to get some movement. We can always edit the amount of movement we provide by changing the noise frequency. So now if I change it to 2.5, you can see that it's changing slightly in terms of how much it's moving by. And if I change the amp by 0.55, you can see that we're getting a lot more movement now. I'm going to go ahead and scroll down and then show you what happens if I change the segments. I'll go ahead and change the width segment, and then now you can see how awkward it is. And if we change the height segment as well, you can see that there's not a lot of movement going on. It's just kind of iffy. So if I add 4 now, you can see that each individual vertex is moving, but then it's not very smooth at all. I'm just playing with these different numbers to see how smooth I can actually get it. Now there is a caveat. You might want to just go, balls to the wall and make it as smooth as possible. Like right now I did 100, but this will eat up your GPU, and in terms of performance, it is not good at all. So right now I'm at 100, extremely smooth, and I love it, but it's just going to eat away. It's not going to, look as good because it's going to be a bit laggy. So I'll set it back to 16, and this is pretty perfect for now. I'm going to change the FOV a little bit just because it's a bit too in my face. So I'll switch it to 12 rather than 10. And there we've got pretty awesome movements. Next, let's get some texture going. We're going to get an image placed on our plane, and we'll see how that looks. Scroll to the top and let's import useLoader from React 3 Fiber. And inside of our wave component, what we can go ahead and do is create a variable called image. This variable will be an array. This will be an array, and we'll assign it to a useLoader. And inside this useLoader, it will take in a 3.textureLoader. And for the second argument, it will take an array of a string of the image path. Now you could use a local image, but I'm too lazy. And what I'm going to do instead is just pull an image from Unsplash. This isn't best practice. Be sure to, use images on your local or your CDN. I'm just pulling it from Unsplash just because it's a tutorial and we don't care too much about performance in our case right now. Okay, so once we've added the image, I'm gonna go ahead and get rid of this wireframe, and then I'll pass in a useTextureProp and assign image to this useTextureProp. Now this prop will be a uniform. So let's scroll to the top, and inside our uniforms, I'll add useTexture, and I'll assign it a default of new 3.texture. Now we need to use this texture in our fragment shader. So what we'll do is write uniform, and then we'll set it a type of sampler 2D, and then write uTexture. And in our main function, what we'll do is create a variable called texture, giving it a type of vec3. We'll then run texture 2D, and we'll pass in our uTexture, and also a VUV so that we can get the right positions. And then outside of that, we'll add a .RGB. Now we'll replace this whole sign and UV time with the texture variable. And if we save, and now you can see that we have an image placed on our geometry. Awesome. So now you can see that there's this whole movement going on. The image is moving, the vertex shaders are moving, but the image isn't really matching the vertex shaders all that much. The whole movement's a little bit off, and it isn't as emphasized as we want it. We kind of want to control the same vertex wobbly effect in our image. So what we need is to have access to this pos.z in our fragment shader. And again, to have access from the fragment to vertex, we need a varying. At the very top, I'll do a varying float vwave, and then I will assign vwave to pos.z inside of our function. And then now we can scroll down to our fragment shader and then write varying float vwave so that we have access to it from the vertex. And then inside the main function, we'll create a float wave variable and set that to vwave multiplied by 0.1. Now we'll take this wave and then we'll add it to our VUV inside of our texture variable. And now if we refresh, you can see that the image itself is just as wavy as the vertex. We can control how wavy we want it. So if I multiply the wave by 0.6, you can see how crazy this thing can get. And if I switch it to 0.4, you can see we have full control of it, similar to what we do in our vertex. Now there's a lot of designs out there where the image itself is wobbly, but not the actual vertex. We can quickly change that by replacing POS in the GL position to position. Again, remember, position is just the static position of our geometry. POS is the position itself getting manipulated with the code that we wrote up top. So now we see that the image itself is just moving, and it's pretty cool. You can kind of get these two different effects of the vertices in the image. Okay, this is a bit too extreme for me. I'll change them a bit so that we have less of an emphasized wobble or wave, and then we should be good to go. The last thing we could do is add a text in the center of our image. So I'll scroll down all the way towards our app function. I'll get rid of the scene, and then I'll put a React fragment. And inside of this, we'll go ahead and add an H1, and as a sibling, we'll add the scene. Then we can add some text. In this case, I'll go ahead and write pomada modeladore, which is hair paste or hair clay, for your hair. Let's go ahead and switch to the app CSS now. And what I could do is just change the background on our body and then add a font family of Avenir with a system font fallbacks. And then just styles for our H1, very basic stuff, white color, centering it into the screen. And then we've got something like this. We can switch over to app.js and add a bit more emphasis on our frequencies. And that does it for us. If you did enjoy it, please leave a like. Don't forget to subscribe if you haven't already. If you have any questions, go ahead and comment and leave some ideas for future videos. That's gonna do it for me. And as always, take care of yourselves out there.